we are going to look at a couple of applications of exponential functions. The first one that we're going to look at is compound interest. So you put money away in a bank account, and if they give you an interest rate, you're going to make money on that. So here we have a little example which says you have $100 and it gets 2% annual interest, and the key thing here it says is that it's compounded annually. So what that means is after they pay you interest, you can now make interest on the interest. This is different than some places give simple interest. And simple interest would mean that you would get that 2% only on your $100 and never on the money you made. And so you always get the same amount of interest no matter what. But compound interest can have interest charged on top of interest. And that's how most banks operate, whether they're lending you money or if you have money in their account. Now, unfortunately, right now, most interest rates in bank accounts, if you have money in a bank account, are really, really low. I think my interest rate is at 0.000000001 because they never pay me any interest. But sometimes a student account, you can get like 1, or I've seen like 1.35%. Still not very big compared to like 20, 30 years ago where you could get bank accounts that paid you 10% interest. So anyways, if you had 2% interest, after 1 year, you would get an extra $2. And then, after 2 years, you would get another $2, plus you would get 2% of $2, which would be another 4 cents. So it would be very exciting because you got extra 4 cents that next time. But each time it happens, you notice that you're going up by 1.02, so it makes an exponential equation. Now, you can read through this example and it talks about different compounding periods, but in the end we get this formula. So you have a certain amount of money that you put in, your starting amount, that is called the principal, and in this formula it tells you that that is A0 or A0. I is your interest rate. N is the number of compounding periods per year. So if something's compounded monthly, then you would put N as 12. If it was compounded annually, then N would just be once. Compounded quarterly, N would be 4 times. And then here in your exponent, you've got N and T for time. So we can use this formula to calculate all sorts of different things. We'll be doing some more examples later on. But right now, since it's a complicated formula, when we go to our first example here, we're going to learn how we could solve this equation using our graphing calculator. So first of all, we have to have our formula. And if these questions appear on your final exam, they will give you the formula in the question. So you need to be able to use all sorts of different equations, all sorts of different formulas, if they're given to you. So this question, principal of $1,500 is invested at 4% annual interest. They would give you this formula and say what the different variables stood for, and then you'd have to be able to use it. You want to find out when the amount is $2,500. So we want to find out when it's $2,500. The principal, the amount we started with was $1,500. The interest rate, and in this formula, interest rates have to be changed to a decimal. So our interest rate is 0.04, is compounded quarterly, which is 4 times a year. So then you'll have 4 for N up there, and we don't know what T is. So right now, the only thing we've been able to do if we were doing this without our calculator is trying to get things to be the same base. And that only works well if numbers appear on our powers chart. But what happens in real life is people don't go to the bank and say, oh, I want to invest $25 because that's on my powers chart, and I want to know how long it takes till I have $625 because that's also on the same powers chart. right? You just have a certain amount of money, $1,500, and you wait till it's $2,500, and they're not on the same powers chart. So all of a sudden, to be able to do this without a calculator becomes impossible. We're going to learn the algebra in this unit, how to solve this. But right now, all we're going to be able to do is solve it graphically. So we go to our graphing calculator. And we're going to type in our equation, 1,500 bracket 1 plus 0.04 divided by 4 bracket to the power 4x. Now, if you have an older TI-83 or TI-80 or a calculator that it doesn't go up in the exponent, when you put two things in the exponent, you will have to put brackets around it. Now, what this is going to graph is we just typed this part of the equation here into y1. We are going to type this part of the equation into y2. If we type both of those, one into y1 and the other into y2, we're going to want to find out where they intersect. When I type y2 as 2,500, does it make sense that that is going to be a straight horizontal line at 2,500? So as far as setting your window up, one thing that's going to be important is if you just have your standard window, which goes from -10 to 10, you're not going to see anything because we need to see 2,500. So for my y min, I'm going to go from -10 just so I can see some negatives. I need to see at least 2,500, so I'm going to go up to 3,000. Again, my x min, I'm going to have -10 to start, and I'm going to see 50 years if that's enough. And do a check, and I might change my window. So I should see, wow. There's one graph, there's our 2,500. I'm not really happy with how this graph is looking right now, but we could find an intersection point. Just going to check if I put everything into my equation right, and I forgot a plus sign. So we're going to go back and insert the plus sign and graph again, and it looks a little bit more reasonable. So there's your money. Here you are starting with 1,500, and it's increasing because they're paying you interest. There's our 2,500. Where they intersect is the time when it's going to be worth $2,500. So if we go second, calculate, number 5 intersect, push enter 3 times, it comes out to 12.83 years. Now to the nearest quarter of a year, what would be the nearest quarter? 12.75 years? If you round it to the nearest quarter of a year. But at 12.75 years, it wouldn't quite be 2,500 yet. But after 13 years, it would be. So this is how we would solve these things with our calculator. We have to be able to graph them. We have to be able to manipulate our window so that we can find that intersection point, and then we can solve. So question number 14 is a graphing calculator one like this that you can solve.